Hi, GoGate Engineering Institute. We carried out the structural design of this swimming pool last time, and we explained certain things relating to the swimming pool design. So you asked if we did check. So this is the swimming pool structural design, which was taken from this example, from this reinforced concrete design text. And then we modeled the swimming pool precisely, as you can see. The dimensions, the isotropic properties of the swimming pool were all modeled correctly. The swimming pool's base, and then we applied all the loads associated with the swimming pool as it was captured in this text. Now we found out that in the course of analyzing the swimming pool, so the lateral earth stresses, the hydrostatic pressure, and then the lateral surcharges were applied to the sides of the swimming pool for the purpose of determining the strength of the wall and base under ultimate limit states. But something was crucial. We observed that in the design of this swimming pool, the uplift limit states as specified in the code of practice was not verified. The uplift limit states conditions was not verified. So clause 2474 of EN 1990 specifies that the uplift limit state, which is a type of the structural type of the ultimate limit state, is a typical example of ultimate limit state. We have equilibrium, we have structural, we have geotechnical limit state, we have uplift limit state, we have fatigue limit state, and the likes. So the requirement to be satisfied is that the destabilizing vertical force, in this case is the uplift, must be less than the resisting vertical force. So in this case, it specifies that the verification of uplift shall be carried out by checking that the design value of the combination of the stabilizing permanent and variable vertical action. So the permanent and variable vertical action in this instance refers to the uplift associated with the groundwater, the soil water. So in this case, the soil water is said to be 300 millimeters below the finished ground level, and then you need to calculate the uplifts. Okay, according to Archimedes principle. This principle was established in almost 500 BC, before the coming of Christ. That's when Archimedes developed the principle of buoyancy. So it specifies that when a body is wholly or partially immersed in a fluid, it experiences an upward force, or what we refer to as the upthrust. An upthrust is the same thing as the buoyant force. Now, the upthrust will have to be calculated on the entire displaced volume, okay, occupied by the swimming pool. So we did that instead. So what was done, so this was omitted in the previous analysis file or the analysis training that was done. So we decided to add it because we noticed that this was not captured in this calculation that was specified on this text. They did not investigate if the geometry of the swimming pool is satisfactory against upthrust, especially when it is shown on this text that the groundwater table is just 300 millimeters below the free surface. So we had to include it in this analysis. I had to do that to resend this video for elucidation purposes. Now, what was done? So we then had to apply the certain loads that were not taken into consideration previously. One has to do with the self-weight of the swimming pool. Okay, so the self-weight of the water inside the swimming pool. So recall that the water is the water level is about 200, the freeboard is about 200. So the depth of water is 1,300 millimeter, which is 1.3. Specific weight of water is taken as 10 kilopascal per meter. So you have that the water pressure at the base is 13 kilopascal. So that's the water pressure applied at the base. Then at the inclined section of the base, you would have to, by linear interpolation, determine what the water pressure would be. Okay, So the water pressure varies from an intensity of 13 to an intensity of 43 kilopascal per meter. This can be seen from here. So you have the water pressure. Remember, we carried out a derivation to show that hydrostatic pressure, as the name implies, hydrostatic is a linear, is an identity mathematical function that varies with depth. So you need to derive what the hydrostatic pressure is along this inclined section of the wall, and then you apply it correctly instead by using the correct load definition. Then we did the same for the other straight section of the base. So this is the water pressure applied onto the structure, which typically is the self weight of the content of the swimming pool when it's full. The next thing we had to do was to calculate the upthrust. So the upthrust caused by the water. So remember, the water level is high. So if you recall, the water level is specified to be around that. Okay. So we determine what the upthrust is at the base of the swimming pool. Okay, so determine what the hydrostatic pressure is. So the hydrostatic pressure at this base times the displaced volume. So to do that, start to beautifully calculate the hydrostatic pressure, the upward hydrostatic pressure along the bottom surface of the swimming pool. So once you do that, you derive the loads and then you apply. Then you now follow the code requirements by determining the destabilizing, this inequality expression to be satisfied. So what it says is that the destabilizing force, in this case, we don't have any live load, we have only the dead upthrust. Okay, this is the design value of the stabilizing force. So design value is the partial factor of safety times the characteristic value. So the partial factor of safety is taken from table A15. For unfavorable permanent action, the partial factor of safety is 1.0. So we did apply that as the destabilizing force. So we had 1.0, okay, as a partial factor of safety. Then the stabilizing force, a load case for the stabilizing force, which in this case is the self weight. The stabilizing force is the self weight of the swimming pool itself. Then we perform an analysis. Let's perform analysis and see the outcome. Now, from your analysis, go to analysis result to check if the swimming pool will not float. To check if the swimming pool will not float, you go to analysis results. Okay. Now, go and look at load case 7, which is the stabilizing force. Load case 7. Load case 7 is upthrust. So the total upthrust we are seeing is 1,371.53 kilonewtons. That's the total buoyant force acting upwards. Then let's go to load case 8, which is the stabilizing force. For load case 8, look at the weight of the swimming pool is 995. So the weight of the swimming pool is less than the upthrust. So it means that the swimming pool is going to float. So it means that the swimming pool geometry has failed under this condition. So the design of the swimming pool will fail under flooded condition. So this is what was omitted in that text, and we have shown from analysis that this will fail. So how do you rectify this? One, you can reduce the size of the swimming pool. So this swimming pool, the width is about 4.3. So you can shrink the size. Remember that upthrust or buoyant force, okay, so buoyant force is equal to the specific weight of water times the displaced volume. Okay, so this is constant. You can work with this. So the displaced volume is reduced, the buoyant force reduces. So to reduce the displaced volume, what you have to work with is either the area or the depth of displaced volume. So if the depth of the swimming pool remains the same, you can control the area by reducing the area of the swimming pool. Once you reduce the area of the swimming pool, the upthrust will reduce. Okay, once the upthrust reduces and you thicken either the base of the swimming pool, then you could have a positive you could have a positive or what's referred to as negative buoyancy. So the weight of the swimming pool will be greater than the upthrust and to be satisfactory. Thank you very much.